So according to BCS classification, if you still remember BCS classification, they classify chemical entities, new chemical entities, into 4 groups based on solubility and permeability. Okay, and if you still remember our previous lecture, we talked about solubility and dissolution. Okay, and how about permeability? There are some physical chemical properties of a substance that is closely related to permeability. That is what you call lipophilicity of a substance. So now we are going to I'm going to introduce to you about partition coefficient and its applications in pharmacy, which is closely related to lipophilicity of drugs. So lipophilicity of a drug can be measured experimentally by distribution of the drugs between two immiscible phase. One's organic, non-polar, and one polar phase. Since they are different polarity, so they are not miscible. You have an organic here, and you have an aqueous in another phase. So you want to measure the distribution of your drug molecule, okay, in between the two phases, and this relative distribution is known as partition coefficient. And how is it related to lipophilicity? So the more the drugs distribute into the organic phase, then the drug is more lipophilic. Okay, so when a drug is added to a mixture of two immiscible liquid, for example here we have a drug of sample A, okay, it will distribute between the two phases and reach an equilibrium at a constant temperature. Okay, so how you measure partition coefficient? The key point will be the immiscible liquid, okay, when they reach an equilibrium at a constant temperature, they will distribute. Okay, so says the organic phase is at the upper part and the water is lower part. If you see A, percentage of A is lower in the organic, so lipophilicity of this molecule, lipophilicity of sample A is very low because it is distributed more in water. So how the drug is distributed between the two layers depend on the affinity of the drug to each layer. Okay, so for example, when you have a polar compound, for example sugar, amino acid, or ionized drug, they will tend to favor the aqueous or polar phase. Whereas when you have a non-polar compound, which is an unionized drug, they will favor to the non-aqueous organic phase. Okay, and the drug will distribute itself between the two immiscible solvents according to the partition law, which stated that a given substance at a given temperature, they will partition themselves between the two immiscible solvents at a constant ratio of concentration, and this is called partition coefficient. Okay, so mathematically how you calculate partition coefficient? So partition coefficient P is equals to the concentration of the sample, okay, in organic solvent divided by the concentration of the sample in aqueous. Okay, so P is the partition coefficient of the substance, and this is the concentration of the substance in organic phase, and this is a concentration of substance in water phase. So how usually you measure the concentration? So after you have introduced sample A in both organic and water phase, and after they have achieved equilibrium, okay, you take some sample from the upper part and some sample from the lower part and analyze. You can analyze using a UV detector to know the concentration of the drug in each phase. Then you will know the P value. Okay, example, consider that you have distribution of 100 gram of drug between 50 ml of an organic solvent, okay, and 50 ml of water, right? So let's say we have 100 mg of sample A, and we have the solvent 50 ml of the organic and 50 ml of the water. When the drug is added to the two immiscible solvent, okay, in a separating funnel and allowed to equilibrate, okay, you allow them, you put sample A and you allow to equilibrate, okay, and when the organic layer is analyzed, so after that you take the organic layer for analysis, and you found that in the organic layer they have 66.7 mg of drugs. Okay, so what is the partition coefficient of sample A? Okay, so this is a schematic of the question just now. You have the organic solvent here, you have the aqueous here, and you put 100 mg of drugs and put inside, okay, and you shake them and leave it to equilibrium, okay. Then you take the organic part for analyze, and you found they have 66.7 mg. So whatever left in the aqueous will be 100 minus 66.7, which is equals to 33.3. So P is equals to the concentration of the drug in organic divided by concentration of the drug in water. So what is the concentration of the drug in organics? So concentration is equals to weight divided by volume. So weight divided by volume. So you have the weight of 66.7 divided by 50 ml, okay, and 33.3 divided by 50 ml. Okay, so what is the answer? So this is the workout of the calculation. 100 minus 66.7, and when you divide by 50 it becomes 1.33, okay, and the concentration in the water phase is 33.3 divided by 50, you have 0.67. okay, when you look at the P value is equals to 1.33 divided by 0.67, which is equals to 2. So log P of sample A, okay, is equals to 2. So usually the log P is used to describe this ratio, which is the ratio between the organic solvent and the aqueous solvent, which is the representative of lipophilicity. And Christopher noticed that most of the orally bioavailable means those drugs that can absorb, okay, through the intestine on the market seems to have the log P value less than 5, okay, most of the drugs. So following the observation that marketed drugs seems to have log P less than 5, here we comes the Lipinski rules of 5. In the Lipinski rule of 5, it derived an easy to use rule of thumb for drug liveliness in molecule after surveying the world marketed drugs, and the rule stated that we should keep the hydrogen bond donor below 5. Okay, for example, OH and NH in a structure, we should keep it below 5, okay, and keep the molecular weight Okay, molecular weight below 500, and log P of the drug should be below 5, and there should be no more than 10 hydrogen bond acceptor. Okay, for example, nitrogen and oxygens. Okay, when you fulfill these rules, okay, then the drug is expected to be well absorbed, right? Okay, however, like all rules, there are a number of exceptions exist. So a drug has to pass through a number of biological membranes in order to reach its site of action. So a number of biological membrane, for example, when you absorb, they need to pass through the intestine, and they need to pass through the blood vessel in order to reach the tissue. Alright, and since the biological membrane are lipoidal in nature, so the rate of drug transfer for passively absorbed drug is directly related to the lipophilicity of the molecule, which is determined by log P of the molecule. So more explanation about partition coefficient. Partition coefficient are useful for estimating drug distribution within the body. When you have high partition function, the drug is more hydrophobic. Okay, it will preferentially distribute to the hydrophobic parts such as lipids by the ear. But if you have a low partition function of the drugs, okay, it is a hydrophilic drugs, okay, and the drug will be preferentially distribute to hydrophilic parts such as blood plasma. Okay. However, so if a compound that can ionize, then the observed partitioning between the water and octanol will be pH dependent. For example, when you have the unionized phase, okay, like this, then they can easily distribute between the octanol phase and aqueous phase. However, if the compound is ionizable, so they will go through ionizable process and they become ionized in aqueous. Okay, and since they are ionized in aqueous, it cannot move back to the octanol phase, so it's very hard for you to achieve an equilibrium between the octanol and the aqueous phase for the unionized form. However, you are able to calculate the distribution between octanol and aqueous of only the unionized phase after the process of ionization achieve equilibrium. Okay, and the distribution coefficient D is usually used in this case when the compound is ionized. It is the effective lipophilicity of a compound at a given pH and is a function of both lipophilicity of the unionized and degree of ionization because they take Ka into consideration. Okay, for an acidic compound, for example, okay, so how you determine distribution coefficient, which is the concentration of the unionized form in octanol divided by the concentration of the unionized form in aqueous plus the ionized form, and same goes to base. So here is one of the example for log D distribution coefficient for metoprolol. You know what is metoprolol? And antihypertensive drugs. Okay, it is ionizable. Okay, so they don't have log P, but instead they have log D, which is pH dependent. So after we have gone through the calculation of log P and introduction about log D, so what are the implications of the two constants? So from a survey of literature, it is possible to obtain some general guidelines about the optimum log P for certain classes of drugs. So when we are trying to design a molecule, okay, some thought should be given to the following. As studies have shown, okay, for optimum penetration to central nervous system, you should have a log P of around 2 plus minus 0.7. All right. And for oral absorption, the log P should be around 1.8. For intestinal, 1.35. For colonic absorptions, 1.32. For sublingual absorption, 5.5, slightly higher. Okay, and percutaneous log P should be around 2.6 with a low molecular weight. Okay. So how log P can be used in formulation and dosage form design? So when you have a drug molecule with a low log P, you can formulate them into injectable. And when they have a medium value of log P, it is suitable for oral dosage form. And when you have a slightly high log P, which is 3 to 4, you can formulate the drug into transdermal delivery. However, when they are having a very high log P value, there may be toxic build-up in the fatty tissue, because when you have a very high log P, means most of the drug distribute into the octanol, which is the organic layer, which is non-polar. So which means the drug is very lipophilic. Okay, when they are very lipophilic, they will stay in the tissue or the cell. Okay, and this is very hard for excretion. So when there's lack of excretion, then you have toxicity, right? Okay, talking about the clearance and toxicity, increasing the log D value is the distribution coefficient. It will decrease the renal clearance, which will cause toxicity. And also when you have high log D, they will tend to be metabolized by in the liver by the P450 enzyme due to the lipophilicity of the drugs. Okay. However, when they have a high degree of ionization, so if you look at the equation of distribution coefficient, when you have a high degree of ionization, means the log D will be reduced. Okay, and the drug will keep outside of the cell and decrease systemic toxicity. Okay, when you have the ionization very high, log D is very low, means the distribution will be mainly to the aqueous, okay, and they will decrease the systemic toxicity. All right, so the pKa range in about 6 to 8 is advantageous for membrane penetration. Okay, pKa around 6 to 8. So what is pKa? It's a pH when your ionized compound, okay, is equals to your non-ionized compound. Okay, so that's why in conclusion, drugs should be designed with the lowest possible log P, okay, to reduce the toxicity, okay, non-specific binding, so that we can increase the ease of formulation and bioavailability. Okay, and besides that, drugs should also be as low molecular weight as possible, okay, to reduce the risk of allergic. So let us recap the point. So we should design with a lowest possible log P in order to reduce the toxicity. Okay, reduce non-specific binding. All right, ease formulation. Okay, increase ease of formulation. Okay, increase bioavailability. Okay, and this is a 4 points that one should try to find a new chemical entity that is having a lowest log P as possible in order to achieve the 4 point here. And in addition, if we can find the drug that they have a low molecular weight, they can also reduce the risk of allergy. Okay, this is the summary of that sentence. Okay, here we end the lectures, and thank you. So we have finished with solubility, dissolution, and partition coefficient and distribution coefficient. Thank you.